The person who announces that it's time to return to the subject is going to study this
Did
one.
you make that?
She guided me.
Yes.
We worked as a team.
Okay.
And the thing is here. So upon photoexcitation, the bond becomes loose, and you see this carbon oxygen becomes like
It's kind of hard to see.
180, so same as like very straight.
No,
Oh yes, yes, please.
please do.
So the goal for Melody is to get help, maybe not for me because I'm a little busy for my postdoc with the potential energy certificate direction and then plug them into MATLAB code. So here are the guidances for for everyone in previous years. You guys are so unique. You selected so unique projects that this. Oh, thank you.
So little.
You can switch them off. It's too good.
Oh, that's actually really like that.
So in previous years, the projects were much simpler and less innovative than those that you selected.
So what you're saying is we should switch our project.
No.
Oh, you gotta see.
If you seek an easier life, maybe. But if you seek for glory, honor, and intellectual satisfaction, then
I need Dimitri to think I'm smart, guys. Yeah, me too.
You need a lot of people to think you're smart.
What's that supposed to be? Yeah, back to the subject. Yeah.
thank you. So in previous, I have a clear mind, but I don't know how to communicate. So this year, the only project that looks similar to previous year's simple projects is a project by Eva. But her project is most complicated because she has an additional degree of freedom, right?
Yeah.
I just worked for several years to develop this like step-by-step protocols, but you all will deviate from them. It's only for information. But if you would have only ground state potential energy surface, if you would need to overcome only one barrier for reaction, then which is very doable with our code, then the project that you voted for would correspond to answering this A, B, C, D, E questions, and then writing paper and presenting it. And we will modify and I will speak more, but if it is one dimension, one barrier, you select different momentum or wave packet to overcome it and see how better or worse overcoming of the barrier depends on the value of initial momentum. So you change initial conditions, answer some questions, and develop the storing figures and analyzing probability to be in the left and right in reactants and products, right? Of course, plotting. By the way, thank you for Sabine homeworks, but and you did literally what is written. But my expectations were that you guys would provide proofs, plots, how the variance depends on time. In those that I got, no one did it. You just answered by words. It's miscommunication because in previous years, maybe we were doing it together in the lab, but everyone was doing only figures and leaving no words at all. And I was stressing them, please write it by words. And now it's written by word. And here are the words, what do you want? Okay, rate of reaction rate. If you have this product as function of time and take derivative, will be rate, right? Repeat many times for different initial conditions. Check whether we are below or above activation energy, right? Rate, reaction rate, change in time. So analyzing, telling if interatomic distance will increase, which will relate to Melody's project and Eva's project, and maybe to Patricia's project. Approximations, so it's more analyzing. Movies will be required for everyone. So if something was not working, just plan on overcoming this barrier.
Plan on it.
What's wrong? And then in papers and presentations, one would need to have some conclusion.
Okay.
So originally this was what I was going to present. It was 2 lectures, 2 hours each, presented to graduate students. Now I'm going to squeeze it into 30 minutes.
Okay.
So, and
Oh, Dimitri, I have a question. When are we gonna give our final presentations? Is it gonna be during Dead Week or during the final week?
probably I would love to have it during that week, but by matter of fact, it will be during the final because I'm always behind and the schedule, and we need more time to complete things.
Okay.
And we'll find whatever is assigned for final, maybe do it in a bigger room to accommodate 60 guests.
How much time are we going to have to present? Is it
5 minutes.
5 minutes like normal?
5 minutes.
5 minutes plus how many minutes for question?
Unlimited.
0 minutes.
I mean, at least
You're
making these other presentations.
Yeah, he's gonna say start timer
Just time.
and then walk up.
I'm gonna get cut off.
Yeah, me too.
I know. Okay, anyways.
Yeah, our presentation was somewhere.
Wait, although we are short in time, we better need to chat because we know that quite a so forth.
Yeah, I love chatting.
So I will maybe I would try to restrain myself from making interviews to save time, although interviews will be much better. So we are studying non-equivalent dynamics of harmonic oscillator, which means it relates very much to your recent homework, right? So you deviate initial position from equilibrium, right? What did you do in the homework?
I have no
We-
idea.
Come on.
We looked at different initial values of the variance.
Yes. And so you let the position stay in the center. But if you would put the initial position away from the equilibrium, it will oscillate forward and back as Elsa thought it was, right? Your presentations. So the wave packet, I can explore delta because it's like Gaussian shape. Right? You saw it.
Yeah.
So we need to prove it by pen and paper, by keyboard and white screen.
Okay.
So we need to see that in the harmonic potential, if our initial condition is Gaussian wave packet equivalent in its shape to ground state, if it is weighted and let it go, it will oscillate, same as volume spring. Okay, so what are our foundations? What did we got before? And let me check if we are on recording. Not that I'm so selfish and love to hear my own voice. But yes, we are. Good. So we are on recording. Our foundation is that you agree to believe that if you look for eigenstate of the annihilation operator, it will be very helpful to solve for this problem. Or oscillating oscillator, or oscillating state of the oscillator, non-equilibrium dynamics in the harmonic oscillator. Okay. Good. What did we? I know it was ages ago. We had a break. We had Friday.
Yeah.
We
Yeah,
had
that was ages ago.
ages ago. We had Wednesday was something projects and homework. So last Monday we did recursion. You remember what?
Yes.
Recursive function.
So what is recursive? What was it related to? I am doing try to go without interview, but it doesn't work.
No, it has something to do with algebra.
It's something with like n+1.
Yes, fair enough.
Okay.
The
A+1.
we were looking for eigenstates of equilibrium operator. We were looking for them as expansion in basis of eigenstates of the right? And the coefficients in front of each eigenstate are not independent, they are related to each other. So Patricia was coming to the blackboard and complaining, like, hey, it should be not n+1 c n+1 related to c sub n, related with c sub a or something like that. And when we play this recursion, it means that as soon as we know that the most junior,
Oh, it's mine, I write it.
most junior expansion coefficients, not we can express all others, right?
Yeah.
And it is recursion. So how does it, what is the difference? Is there anything different?
Finish me? Oh, it
I
is
would like
ridiculous?
to have something ridiculous.
Oh, sorry, it's
So,
ridiculous.
what is the connection between this recursion eigenstates of the isolation operator and
Wave packet.
oscillating wave packet?
Um,
By now you can say no, nothing, or I haven't observed
No.
anything, even if there is something, it's too big bridge between these two companies.
I would say I haven't seen anything, but I'm assuming it has something to do with. And like being that it's n+1 for recursion,
Mhm.
it somehow fits into like. As time goes on, or like whatever, like your wave packets like going to change the shift,
Okay.
something like that.
I will try to do
Oh,
many things. There will be two big things and few small.
okay.
Small thing will be to normalize wave function and then practice. Remember our third wave fusion.
No,
You were representing it.
Boys. All
You.
of us? Me?
You all. It was part. And
predicting the
if
future.
it would be an exam that you would against, everyone would remember the middle of the night and report it. But I know that I'm just surprising you by unexpected questions.
Third way to predict the future?
What are the first?
Like time.
So if you know that if you know eigenstates, time independent.
You can find time dependent.
Yes, by taking like expansion coefficients from initial condition and then allowing phase accumulation for each eigenstate according to its eigenenergy. I know that some of you hated the word phase accumulation, but I know-
Yeah.
now you remember. So through phase accumulation in the black
Oh,
red red boxes, they communicate the thing that I'm trying to mumble maybe in more efficient way.
okay.
So we do have eigenstate of the integration parameter, and by now we were not including time. But if we let each expansion coefficient to accumulate space according to energy of this eigenstate, then it will be time dependent thing. And we will see that even if you launch this time dependence, this state will state will still be an eigenstate of an integration operator. So it is a little surprise. Most of eigenstates are, especially if we are speaking about Hamiltonian, they're stationary. They accumulate space, but they do not change their shape. And coherent state, I'm just running ahead of myself, the eigenstate of an integration operator, even if you launch the independence, if you move dramatically, but it will stay an eigenstate of an integration operator. So time-dependent eigenstate, which is a surprise. And Roy Glauber with Nobel Prize for it. So we are doing. I'm okay. Those were one big thing. Another big thing, it's still boring expansion coefficients.
Yeah.
Where is our motion?
On the axis.
Yes, but how do we do literal mathematical progression? There are two things. Two ways.
Ways.
One way is to multiply each expansion coefficients by space-dependent eigenfunction, add them together, and see evolution time, same as we did for camels. Right? This is very doable, and this is like standard way, which is acceptable. But it will be boring, like those special functions, we need to take them together with summation of this. It's doable, but boring and complicated. There is a shortcut, there is an elegant way. And now I'm going to communicate the main idea of today's meeting, even if you miss something in the question. Maybe 20 seconds preparation, then they
Timing.
thank you. We found eigenstate of annihilation operator by Dirac representation in the space of expansion coefficient. But you can find eigenstate of annihilation operator in the Cartesian space using annihilation operator as differential operator. This was the main idea. This idea was already practiced in the past. We were finding the solving differential equation for the ground state. We were applying annihilation operator to unknown function and making it equal zero. Remember? And we found Gaussian shape. Okay? Now we are going to apply annihilation operator to unknown function, and it should be equal to unknown function. And by solving this equation, we hope to get this. Probably, although it is all doable derivations, I will be rushing through slides like crazy. It's the worst pedagogical thing because it's 95% probability. When you leave the class, no one will remember anything. But you fail the.
Yeah, that's still 5%.
Let's fight for the 5%. Okay. And at the very end, and during the last 3-5 minutes, there will be a little practical challenges for me to follow my own slides because there will be several substitutions just to get from differential equation to an equation that shows this in mathematical form. That I cannot carry them in hand, but if I derive on the blackboard, I have a cheat sheet. Now I'm trying to understand my own cheat sheet on the slides. So what is the expected answer? What should we get no matter what by in 20 minutes? You should get the Gaussian distribution, exponential to the power minus square of something, right? And square of something, typically we had x squared. And it was Gaussian shape centered at 0. But if you have square of x minus something, it will be centered on something. Okay. And if this something is not a constant but time dependent, that means that center of our Gaussian distribution will be moving. So if this
Something.
will be assigned an oscillatory function, it means the center of Gaussian distribution will oscillate back and forth. So basically, we need to prove that we can get Gaussian distribution that oscillates back and forth because the center of distribution is the trigonometric oscillating function. Good. So we bien sûr.
I have no idea.
We were
I don't speak.
Me too.
Sorry, must be 10.
Which camera? Oh, if I'm showing slides, we still can focus on you guys, right? Okay, so here So the yellow box is what we are going to get. You see, it is x minus something in the power of exponential, right? And this is an equation of oscillating. Yes, so it's wave function absolute value squared. Yes, exactly. And x of t is in the bottom. Okay, start, set, go. So here is your favorite recursion, right? Junior depends on senior. And you see this mu coefficient and square root of n plus 1. I haven't done the normal. Sorry. I haven't done the normalization. It's a little technical detail that maybe we don't need for the class, but we need for just foundation of our education. If any of you will do series or take advanced course that thing that future. So wave function absolute value squared must be integrated over everything should be equal to 1, right? Who loves normalization? Who was asking questions about normalization? Patricia. And capital. Should be 1 or whatever. If we are not in the Cartesian continuous space, but if we are in the space of in Dirac space, then normalization is read as C naught star C naught plus C1 star C1 plus C2 star C2 and then equals 1, right?
Yeah. So
we take the expansion coefficients from our previous time that were obtained through recursion, right? It means that all coefficients do depend only on C naught. And we can put C naught outside of the brackets, and then remaining thing will be power of this mu proportionality coefficient, and we have this factorial. I have the square, and factorial without square root because we have absolute value squared. Now, if we arrive to this expression, we return back to your favorite calculus 1.
Yes.
For progression. So if you see that 1 plus x squared over 2, you recognize, oh yes, it is an exponential.
Yeah.
Right?
Yeah.
You do. So this series can be added together as e to the power mu squared. So 1 from normalization is product of most junior coefficient squared times this e to the power mu squared, where mu squared is let me jump back one slide. I know that some people are very nervous if someone doesn't, so I will return back.
Yeah, I hear that.
So mu is our eigenvalue that we used, and it is used here. So this mu comes into our normalization, and then we can solve for C naught. So if you assume that we do not have any complex that C naught is real, then we can solve as a square root of this thing. And square root means power 1/2, right? And then so C naught is e to the minus mu squared over 2. Mu squared is eigenstate. So we started eigenvalue. We started from eigenvalue, and now we do have C naught, and we can obtain from most junior coefficient all senior coefficient. So we have solved for eigenstates of the integration operator. We have that state. We can add to this expansion coefficient. So we have summation, we have coefficients, we have eigenstates, and now we add accumulation of space as a factor. So E sub n for harmonic oscillator will be h bar omega n plus 1/2. Right? So if you plug this one into here, we will have time dependence. So plugging this time dependence into eigenstates as they develop over time. So here is how single eigenstate is evolving over time. So this is minus I for H bar is at MT. So H bar in the energy and in the definition cancel, right? And then we have frequency omega t, and then we have number of eigenstate. Okay. If you feel that it is either boring or you lose track, just do some signals, because there is no reason for me to speak if you're not follow. So you better delay or do it different time rather than missing.
I'm following.
Thank you, Rashid. So one can chop as a product. So this thing will be the same for any eigenstate, and this one will depend on the number of them, right? Now we are going to plug this time-dependent eigenstate into here. So here is our eigenstate of annihilation operator, and we compose it as eigenstates of the Hamiltonian, right? With time dependence. So
What's mu?
mu
It's the eigenvalue. No.
I'm going just to make sure. Let me go back.
That's not
So
This one.
a dagger psi equals mu psi. So we will look at eigenvalue of annihilation operator. Okay.
That was my postulate, was like this similar to that.
In postulates, we were which number?
One with like the like average value inside.
wasn't it? You had 4 and 5.
Yes.
Something like
Maybe
that.
maybe observables.
Yeah,
So by finding results of measurement for certain observable, one needs to get eigenvalues of this observable and collect them. Yes, it is related. So back to boring math, or maybe fun math. So this common factor can be put outside of the brackets. This thing comes from normalization that we got on the previous slide, right? And here we have an interesting and appetizing progression. So time independent eigenstate, accumulation of phase which is proportional to the number of eigenstate, and then the expansion coefficient that we derived through recursion. So there is a very interesting observation. Here we have mu to the power n, and here we have e to the, like this exponential can be expressed as e to the power minus I omega t to the power n. Do you see that these two things that I they're the same, right? And now we can see that mu to the power n and then time-dependent exponential to the power n. Why don't we combine them together? Mu times e to the power minus I omega t and then power n. And then the rest is as prescribed. Now, if we compare top line and bottom line, we can see that bottom they are equal if you redefine u bar of t as this thing. So if you say that eigenvalue of annihilation of the operator is time dependent and accumulating phase with frequency omega, it will still match all derivations. It will still be the same function form, it will be the same coherent state. Okay. Good. About half done. So 8 minutes for if we go forward in time, we just accumulate phase, complex phase. And then we can, it is related to several ideas. For example, if melody wouldn't have dissociated curve in the upper potential, but if it would be like harmonic, then promoting from ground state to upper state, it will launch oscillations. And it is how these coherent constellations are often prepared on experiment with femtosecond later. Okay, so getting to this thing. Initiation operator acting on an unknown function. Instead of mu, I use gamma because I let's say cheated, copy pasted from a text, and I just forgotten to share, but it's the name of the author is very similar to the name of the little animal that climbs on trees. Squirrel. The squirrels.
Oh, I see.
Yeah, it was written, it's written somewhere.
Oh, yeah, okay. I always fear to make an error and therefore trying to not to write it because not to offend the author or the animal. Okay. And I hope he will not watch recording. So instead of u, here is gamma. Here is our initiation operator in Cartesian space. So it is one thing that you did a little quiz, right? So linear combination of position and momentum, I in front of momentum, combination of constants in front and omega in front of x. And if one does combinations of all these things, yes, it is here. So one can redefine this combination of fundamental constants and frequencies into new variable just to save time on effort in writing symbols. So if we look on this definition and this thing, then the x is inherited from position, ddx inherited from momentum, and we see that because of this m omega, they have sigma variable in numerator and denominator. So you want to believe it? Anyone wants to oppose it? Okay, good. Now we need to act by this initiation operator onto a known function. And this is something that if I would have at least 10 minutes more, I would either direct myself or direct some of you because it is something I know we all can do. So x d psi dx. So there is only one derivative, one dx. So if we move the increment, multiply everything by it, and divide everything by psi, then we will have from first term we will have x dx. The following. From the second we will have d psi divided by psi, and here we will just integral of dx. So by integrating, it will get x squared from the first term, log of psi from the second, and linear x from the last. So we need to solve for psi. If we just plug this thing into the power of exponential, right? We will have that wave function is equals to, you see this minus x squared plus gamma x, so it is second order polynomial. And gamma is our mu that is time dependent. So in some sense, it is already an answer, but it is not pleasant, it's not visual. So we want to bring it into the shape of x minus cosine omega t squared, right? So we want to identify full square, and we need to add and subtract the, if this one will be a squared, this will be 2ab, and then we need b squared plus and minus b squared before. And this will add normalization. Then instead of psi, we need to look on absolute value of psi squared. Okay. Oh, down, generously. So, in the complex conjugate of the wave function, everything that had imaginary unit will swap the sign, including the factor gamma, which is our mu, which is eigenvalue. We know that it accumulates phases, it has imaginary thing, therefore we need to put a little star. And when we have wave function without conjugation, it is I omega t. When we have this conjugation, it will be minus I omega t. Right? So from psi and psi star, you will have the this is psi. We will have two wave functions. And the difference is only in this gamma term. Once it will have accumulating phase in positive, and another time accumulating phase in the negative direction. Everything is the same. When we multiply them, then we will have linear term with gamma and gamma star. And there we will be able to apply Euler function, Euler formula, because accumulating in the positive and negative direction will give us a cosine. Okay, and this thing that I called theta here, in fact, it includes omega t, so it will be cosine omega t. Okay, so we think with cosine omega t, and then we need to identify what was the A and what was B. So if X over sigma is A, then the rest two gamma naught cosine will be equals to B, right? And we just need to add and subtract the thing and put it. Let's and combine it. You look right, and combine it into this P of xt. So you look right, bless you, you don't right. So if we have this b squared added, then we have square of subtraction, and we have what we need, x minus cosine, right? And this thing will be related to normalization. So normalization will be time dependent, which is okay. But in fact, we are arriving, and if we will redo normalization and check how things change over time, this functional form will be correct.
Right on time.
Yay.
Hey,